Okay. So I want to welcome you to this topic 8.1. Topic 8 is a really special topic in the IB curriculum. It uses physics, and it's definitely related to physics, and we'll learn some new physics even. But it's the most applied physics topic that we have. And it shows how the understandings of physics and the work that we've done over the last several months connects to engineering, specifically how we design and analyze the systems that we use to produce power in topic 8.1, and how it applies to understanding the Earth system and the greenhouse effect, which is what we'll look at in topic 8.2. So these are really interesting topics, in my opinion. The big idea that we have for topic 8.1 is that humanity's need for energy sources is one of our driving uh, motivations for engineering. Uh, we have to find sources of fuel to produce energy. New devices require energy, and this is an area of rapidly changing innovation. We'll be looking specifically at energy production from traditional sources like fossil fuels and also renewable sources like wind and hydroelectric, and also nuclear fuel sources. So we'll connect to a lot of the other topics that we've already studied. And we'll also look at how energy engineers would analyze those systems. To start with, I want to quickly review many of the different forms of energy. I won't read everything that's here, but in terms of these different forms of energy, we've looked at nuclear energy. When we talked about nuclear energy in topic 7, we were trying to understand how the nucleus, when it changed from one nucleus to another, would release energy, that binding energy that's associated with the changes in mass. When we talk about nuclear energy from the perspective of power plants, we're normally talking about fission based power plants that use heavy elements that undergo spontaneous fission when they are bombarded with neutrons, things like uranium. Chemical energy, you've looked at previously, not specifically in this class, but when we talk about reactions that take place, particularly combustion, the interaction of, say, a glucose internally to humans or plant cells, where glucose is combined with oxygen to release energy, or any combustion reaction, is what we think about with chemical energy. And these are going to be important reactions to apply to fossil fuel power plants. The next few, 3 through 6 here, are more often associated with the renewable sources and as intermediate sources of power and forms of energy. Thermal energy, the random motion of objects at high temperatures, that we studied in topic 3 as the random kinetic and the potential energies associated with objects, will in this topic become an intermediary between, say, nuclear energy or chemical energy that is burned or releases energy into a liquid that is used to turn a turbine. Uh, Bulk kinetic energy and bulk potential energy are energies that are associated with fluids when they are moving in a coordinated way or located in a particular place. So with bulk kinetic energy, we're talking about the motion of air, like wind, or we're talking about the motion of water, like tides or rivers. Bulk potential energy, we're talking about mass that is raised up off of the ground. Water in dammed rivers is the main example that we'll think about here. Uh, when we talk about solar power, we're talking about energy associated with light. We've talked about this in topic 7. The collection of photons has energy that can be passed on to other objects, either in the form of thermal energy or directly to electrical energy. And electrical energy down here at the bottom is probably the one that we are that's most important because it is the primary secondary form of energy that we use for powering computers, that we can use to power cars. It is a very it is a very useful form and transferable form of power, but we get very, very, very little of it naturally, and we don't know how to harness lightning bolts. When we think about energy in terms of power sources, we can split them into a couple of different groups. Primary versus secondary energy. We're talking about, is this a form of energy that can be harvested and is not processed or ready to be used? This would include fossil fuels. Oil is a big store of energy, but it's not directly usable for its energy benefit. Same thing with nuclear matter, or even wind and solar, unless you're going to go and stand out in the wind to cool down or stand in the sun to warm yourself up. These are not directly usable for civilization for the purpose that we need energy. Secondary energy, on the other hand, are the intentionally processed forms of energy, electricity being the primary one that we'll think about. But thermal energy is used in engines like combustion engines to produce motion. So this means that energy has been processed and is intentionally getting ready for use. Renewable energy and non-renewable energy is a classification of energy having to do with whether the resource, particularly the primary energy source, is a finite resource or something that can be replenished constantly. Solar energy, the light from the sun, is what drives all of the renewable energy resources. So things like winds, things like the water cycle are what we think of as renewable energy. Some exceptions here. Tides are driven by the moon. We think of that as a renewable energy source. And most people even consider geothermal energy, which, even though eventually the core of the Earth will cool down as the radioactivity of the core of the Earth is depleted, it's going to take a very, very long time. And the temperature underneath the surface of the Earth, where we usually harvest geothermal energy, will stay warm for a very long time. So we call that a form of renewable energy. Non-renewable energy, the primary thing we think about are fossil fuels, natural gas, oil, but also nuclear matter is also finite in the sense that there's only so much of it that we can harvest it, and it is generally on Earth being depleted faster than it can be replenished. Fossil fuels do replenish as biomass decays under heat and pressure to form coal and oil, but very, very slowly compared to the rate that we consume it. So those are just some definitions here. In terms of the calculations or the problem solving that's done in this unit, two terms, specific energy and energy density, are important to learn and understand the distinction between them. These are used to quantify the amount of energy that's stored in non-renewable fuel sources. So how much chemical energy do you have in a kilogram of coal? That would be the specific energy associated with coal. And we see that that's 3.2 times 10 to the 7th joules per kilogram. So if you can do problems where you figure out what mass of coal can be carried on a train to a power plant, and that can help you understand how much energy can be harvested from that mass of coal. On the other hand, energy density is looking at the energy per unit volume that can be produced by something. So we're usually talking about a meter cubed for the SI unit. For many of these, those numbers are just a ratio apart, the ratio being the density of that material. But in this table here, you'll be able to see some patterns in energy density and specific energy. So if you pause and take a moment to look in the specific energy for patterns or differences, take a look in the energy density for patterns or discrepancies, and then I'll mention a few of them. You can pause now and look. Okay. The key difference here that you'll probably notice is uranium is much, much higher by several orders of magnitude, like 5 orders, almost 6 orders of magnitude when we talk about the specific energy, the energy per kilogram, and by almost 10 or 11 orders of magnitude when we talk about the energy density. Got interrupted there for a moment. Let me see if I can catch back to where I was. So several orders of magnitude greater for uranium. And that's, of course, because it's a source of nuclear energy. And the energy associated with the nucleus is, and the strong force is much, much, much greater than the energy associated with chemical bonds that's associated with the electrostatic force. So that's that one. We'll leave that off to the side. And then we notice that the specific energy per kilogram is relatively similar for many of the different hydrocarbons, whether that's natural gas or kerosene, diesel, or coal. Hydrogen gas is being considered as a cleaner form of energy because the combustion of it doesn't produce any greenhouse gases, it just produces water. And it actually has a slightly higher specific energy because of how light hydrogen is. On the other hand, we can take a look at the energy density and the big discrepancy that we see here between hydrogen and natural gas, and gasoline, kerosene, diesel, and coal is, of course, that these two are gases, and so they have much less energy per cubic meter than the solids or liquids, and that's just primarily because they have a much lower density as gases. The trick in terms of the IB between these two quantities is that specific energy and energy density, neither of these formulas appears inside of your data booklet, and it's tough to keep specific energy straight with mass, density straight with volume. So a little practice on that would be good. I encourage you to follow this link to get to the interactive version of this data that looks at how global energy consumption has changed over time. The page that's there goes into a lot of detail about how these changes are measured and how things have been changing, particularly in the last 50 years or so. The data is a little old now. Some of the things that you may notice here are, of course, that over the last 200 years, energy consumption globally has increased more than tenfold, starting particularly at the Industrial Revolution. And then with the advent of widely available electricity. So the demand for energy has grown and grown. And this curve also is driven by the relative affluence of human civilization as more and more people move to cities where there is access to all of these things that happened in the 50s to the 90s and early 2000s. The other thing we notice is the recognition that oil and coal are limited and finite started to lead the drive to renewable or alternative energy sources. But even though a lot of technological advances have been made in these areas, they still account for a very, very small fraction of our energy portfolio. So taking a look through there and learning a little bit about the stories of energy and how energy consumption has changed would be a really good thing to do. Let me see if I can. It's you can see at the bottom here, ourworldindata.org is where this data comes from. Oh yeah, here it is. There's the link there. Power production involves the conversion of energy from one form to another. Uh, and as we've learned with, say, a skater going up and down a ramp, that energy conversion from, say, potential energy to kinetic energy is never 100% efficient. We think about friction as converting some of the kinetic energy into thermal energy that is dissipated or wasted. And the same thing is true inside of power plants. And following that energy to see where those inefficiencies are, to see where the energy is lost, because of course it's never truly lost, it's just converted into a form that we can't use. Uh, Engineers use what are known as Sankey diagrams. And a Sankey diagram is usually read from left to right, where energy or whatever quantity is being studied is starts off in one form and then is generally converted along with some losses. This diagram is showing those losses all in red for a coal-fired power plant, leading to the energy that is necessary to, say, illuminate the page in a book. So here we have 100% of the energy, or 100 units of coal, inside of the power plant. 35 units are converted into electricity, and 65 units are lost during power generation to thermal energy. This is typical for a coal-fired power plant. The transmission, distribution, wiring, all of those lead to some losses, as we'll study in topic 11, I want to say, that that lead to this 35% being depleted down to about 31% before it reaches a customer's home. This is an example of a conversion from electrical energy to light using an incandescent light bulb, those hot filament bulbs that are very, very energy inefficient. The 31 units of energy, we get about 10% useful light out of that, and the other 90%, or 28 units, get converted into heat. And then some of that light can't get used by you to read. Some of it goes into the lampshade or reflects off the walls where it doesn't get used. Some of it is just idle where the light is on and nobody's using it. And ultimately, we have the 1 unit of illumination. Sankey diagrams are helpful in trying to identify places where innovation can help. Obviously, innovation inside of power plants looks to convert larger quantities or larger percentages of energy into electricity, but also innovation in lighting. So LED bulbs, fluorescent bulbs are a technology that allows much more of the electricity to be converted into light. And so innovation exists here. And then, of course, idle things like leaving the lights on when you leave the room can be changed with behavior. As you go along, of course, you can always calculate percentages here to figure out how efficient something is. And these efficiency calculations are the second type of calculation that are often done in topic 8.1. Efficiency, as either with power or with energy, is done as the ratio of, say, secondary energy to the primary energy. How much electricity do you get for how much coal? It can also be done in terms of power, the power out, or the useful power over the power in. So here we have maybe a little more detail into a fossil fuel powered turbine. So we have the fuel oil here with 274 megawatts of fuel oil. MWE is a megawatt equivalent, converting everything to electricity units. The boiler burns the oil, converting it to steam rather efficiently here with very few losses. You can heat up water. The turbine, on the other hand, is only about 60. Is only about 30% efficient. So you have 62 units of energy, 172 units of energy that are lost to the condenser for every 72 units of electrical power produced. And so all along the way here, you can do calculations for the efficiency. You could look and say, how efficient is the boiler? We have 246 megawatts coming out for 274 put in. So this is a 90% efficient boiler. Pretty good. The steam turbine, on the other hand, for the 246 units in, we have 71 units out. So a little under 30% efficient. Or you can do over several steps at the same time. So for the whole power plant, you could look at the energy in 274 megawatts, and out you have 72, which is a 26% efficient. So looking through these calculations and understanding and interpreting Sankey diagrams to give efficiency calculations is the other type of problem that you commonly do in this topic. The remainder of this topic, the sort of second half, looks at the specific types of power plants and their relative advantages and disadvantages. We're going to start off with two non-renewable power plant sources. These are the ones that are the most common. So we're looking at coal-fired power plants or oil or natural gas. And then we'll talk about the modifications that are necessary for the use of nuclear fuel. This diagram here is representative of what you would generally look at. Inputs to the system are obviously the fuel source, and this could be coal or oil or natural gas. All would be approximately the same. And you need some source of cooling. Usually a river is used because it provides a constant source of cool water. Burning the coal is pretty obvious. It produces, obviously, carbon dioxide and water, as all combustion does. And that's used to boil water. Usually that water is in a closed loop and it's not directly sent out to the river, raised to very, very high temperatures, where it is fed into a steam turbine. As the steam pushes on the turbine, it cools, usually but needs to be condensed by being exposed to cooler temperatures. So this is where that major inefficiency comes in, is that you're able to harvest about 30% of the thermal energy of steam with a turbine, but the other 60% is essentially going to heating up a nearby river. The condensed water gets sent back to the boiler to be heated up again. The turbine, as it spins, turns a generator, and the moving magnets inside of a generator produce electricity, as we'll learn about in topic 11, and that's sent to a transformer and ultimately to power lines. So in terms of your Sankey diagram, we can compare what we see here to what we saw on the previous slide, where you have fuel coming in, the boiler producing steam, and the turbine producing electrical power. So we have the coal coming in, the boiler producing steam, the steam driving a turbine to produce electrical power. When you work with nuclear fuel, combustion isn't the way that steam is being generated, but you are still working with all of the main parts of a steam-based power plant. It's just that the thermal energy is coming from nuclear fission. So nuclear fission, you have fuel rods. So fuel rods would be those that contain the fissionable material, although usually it doesn't undergo spontaneous fission. It's usually fission when it's exposed to or bombarded with relatively low energy neutrons. The fission of the nuclei releases additional neutrons, and those neutrons go on to hit nuclei inside of the other fuel rods, creating what's known as a chain reaction. So, one neutron, for example, might cause a nucleus inside of this second fuel rod to undergo fission, releasing 2 or 3 additional neutrons, which may bump into these other fuel rods, ultimately releasing more and more and more neutrons, which can be a runaway problem. The control rods that can be raised or lowered are going to absorb those neutrons and prevent that chain reaction from running away and producing too much energy such that it damages the power plant. The term critical mass refers to how much of the fissionable material you have inside of the fuel rods. The control rods can be lowered all the way down to reduce the amount of fissionable material you have in one region to prevent it from undergoing fission, or removed to reach that critical mass where fission is occurring in this chain reaction. Surrounding the fuel rods is what's known as a moderator. The moderator plays 2 roles inside of a nuclear power plant. The main role, as you see it cycling through here, is that it's absorbing energy from those high energy neutrons, and that energy is heating up this moderator, this coolant, and is being sent over to raise the temperature of water to turn it into steam to ultimately drive the power plant. The moderator generally plays another role as well, and sometimes there's a second moderator involved that's not a liquid, and that's that the neutrons that are produced by fission are often very high energy, so high energy that they don't interact well with the fuel rods to create that chain reaction, and they need to bounce off a few other nuclei to slow down a little bit, transfer away some of their energy before they interact with another fuel rod, so that they can cause another fission reaction. So the moderator is important to slow down the neutrons to allow fission to take place. And in the process of slowing down those neutrons, it absorbs the energy that goes into the steam generator as well. I think that covers the basics of a nuclear power plant. Your textbook has some more details, be worth taking a look at. When we talk about the risks and rewards of fossil fuels and nuclear fuels, they'll sound similar and different. The advantages of fossil fuel plants are that we have an extensive network of power plants in place in most countries that allow for fossil fuels to be used pretty much where they are needed to produce electricity for communities. It's a relatively well-developed technology with a variety of different power plant styles to use a variety of fossil fuels. Relatively cheap and high power output because of the high energy density of fossil fuels. Disadvantages: they are non-renewable, so they will eventually run out. We also recognize that they produce a good deal of pollution, specifically carbon dioxide. But previously, they've also caused problems with acid rain and other byproducts. And the carbon dioxide in particular contributes to the greenhouse effect. In terms of nuclear power, again, the high power output is probably the biggest advantage. And we also have relatively large reserves of nuclear fuels because we really haven't been using them as a civilization for particularly long. Nuclear power plants have the additional benefit of not producing greenhouse gases. However, they do pollute. The waste products can be very, very difficult to dispose of. At the moment, we just have storage for them, but not really a good way to process that waste. So it's piling up the way that all garbage does. Ultimately, they pose a pretty big health hazard if something goes wrong. Fukushima, Chernobyl, 3 Mile Island are all notable historical events where nuclear power plants have failed and produced public health risks. And the problems associated with mining are also pollution. And of course, one secondary use of nuclear power plants is that in addition to producing fission, those heavy neutrons can be used to produce material that's used inside of nuclear weapons. Also in medical devices, but nuclear power, many countries that have nuclear power programs worry that countries that are developing nuclear power programs may be looking for the secondary benefit of producing material for nuclear weapons. Moving on to the much greener renewable energies, we have solar power. Solar power generally is thought of in two different forms. You have solar thermal energy, illustrated here on the right, where sunlight is used to directly heat some sort of liquid that is pumped through and used as a boiler. There are these large power plants that collect solar energy and focus it using mirrors to liquefy sodium, and that sodium just essentially drives a steam-powered turbine. Very safe and relatively inexpensive to produce for power plants. On the other hand, much more recently, solar panels are used to directly convert sunlight into electricity. These semiconductor-based panels work via something similar to the photoelectric effect that we'll study in topic 12 to push electrons off of one surface and onto another surface to directly create a current. These are the solar panels that you maybe have on a little calculator or on the roof of your home. A second renewable source of energy is hydroelectric power. Hydroelectric power is particularly interesting because of its ability to be used as a storage of energy, what's known as pumped storage. The basic idea of a hydroelectric power plant is that a large mass of water is essentially a source of stored potential energy. That potential energy can be converted into kinetic energy, either by exerting pressure on water that's down low or by flowing downhill. That kinetic energy can then be used to drive a turbine directly. Down here, we see a schematic of essentially a dam. You have a reservoir. There's the dam that gives you an output of water down low. The output turns a turbine and releases the water to a river or to, in this case, a lower reservoir. The power associated with this, the power generation, essentially has to do with the flow rate of water. The volume per unit time can be converted into a mass per unit time by multiplying by the density. And then you have this rho VGH, which is essentially MGH per unit time. So it's like potential energy divided by time is the power. Ultimately, if you produce power for a long period of time, that reservoir empties out. Hydroelectric power is considered renewable because when sunlight hits water, it goes through the water cycle, and ultimately the rain will bring that water back up to the upper reservoir where it can be emptied again. In a pumped storage plant, instead of using the water cycle, you use power that's been generated frequently by wind or solar, power sources that are sporadic and not always operable. Solar panel only works during the day. But the power is used to drive the turbines in reverse, filling up the upper reservoir when the sun is out, and then running in the forward mode, in the generating mode, at night when the turbine then produces energy to send out. So similar to a rechargeable battery, you can put energy in and then have that energy taken out again later. So a pumped storage facility can kind of act as a battery for a solar power plant if you can build one. And the last form of renewable energy that we'll look at, whoops, I have to shrink because that equation is wrong if I don't shrink myself, is wind power. Wind power is now the fourth time we'll talk about a turbine, but it uses the turbine, it moves the turbine directly. So if you point a turbine into the wind and it turns, it can power a generator directly. If you have a windy area, these can be very, very useful to power the grid. The power here, an interesting fact, you see the density of air, obviously, and larger cross-sectional area turbines obviously produce more power. The interesting thing is that the power scales as the cube of the speed of the wind. And what this means is that if you have a particularly windy area where speeds are very high, you can produce an awful lot of power. But as the wind dies down a little bit, if the wind speed is cut in half, the amount of power decreases by a factor of 8. So the wind turbines can really only work when you're at high speeds for the wind. And that closes this. Oh no, sorry, one more thing. So relative advantages and disadvantages. All of these renewable energy sources have the same basic advantages. They're essentially free in that the primary energy source is not owned by anyone. Nobody, well, rivers to some extent, but nobody owns the wind, nobody owns the sun. They're inexhaustible resources. So once you've produced the power plant, apart from upkeep, they're relatively inexpensive, although sometimes developing them can be quite expensive. Wind and solar have disadvantages that they're dependent on local conditions. If it's not windy, then you're not getting any wind power. If the sun is not out or it's cloudy, you're not getting very much solar power. On the other hand, hydroelectric power is much more reliable, but only works in very specific locations where you can have a reservoir. Hydroelectric and wind have some aesthetic problems. There are a lot of changes to the environment that come from building a hydroelectric plant, backing up a river. Oftentimes, communities along the river are destroyed and sunk underwater. And many people don't like the aesthetics or the noise that's associated with wind power. So those can be problems with convincing people to use those who are used to having the relatively quiet and non-invasive energy associated with fossil fuels. Solar power seems relatively advantageous. However, the initial costs are quite high, and they require a very large area of solar panels to produce any appreciable amount of electricity. Most people cannot even successfully power their homes with solar panels covering their entire roofs, and so it would take a lot of materials harvesting in order to create solar panel to not just drive household use, but also industrial use. And that brings us to the end of topic 8.1. In terms of things that you'll want to do, there's definitely some problem solving associated with specific energy and energy density problems, so you should practice there. Interpreting Sankey diagrams and doing efficiency calculations are also important. The quick overview that I've given you to the different types of power plants and their relative safety covers a lot of the high points. Maybe you knew a lot of those things already, but the reading inside of your textbook can be much more helpful. And then I can't stress enough how interesting that our World in Data website is to take a look at how human civilization over the last 200 years has really changed by our ability to um, work with primary sources of energy and particularly to produce electricity. Thank you for watching.